Hello everyone, welcome back to my channel, Predicting the Future. Today we're gonna continue from our last video where we talk about tail sigma fields, and today we're gonna talk about a theorem called Kolmogorov 01 law, which will talk about what happens of tail sigma events in the tail sigma fields when the random variables are independent. So that will be our Kolmogorov-01 law. Before we talk about that, I have to introduce some of the definitions and theorems that we're gonna need to prove the Kolmogorov-01 law. So let's first talk about what is a Kolmogorov-01 law. So suppose x1, x2, and so on are independent random variables, and an event that belongs to the tail sigma field of those random variables, then the probability of that event A will be either 0 or 1. So the far remote event of a random process is of that tail event is either happens or never happens. So there's no like probability 1/2 or something. So that's what it tells us for Kolmogorov-01 law. And before that, we need to introduce um, some definitions. The first one I have to introduce is what is a pi system. So a collection is a pi system if it's a closed under intersection, which means that if A and B belongs to the collection A, then A intersect B also belongs to the collection A. That defines a pi system. And when we talk about uh, random variables, we usually will include the whole space omega into each pi system, because it doesn't really make any difference by including that whole space into each of the pi system. And then we're gonna introduce the independent pi system theorem, which we won't be proved, but it's very important one. So the independent pi system theorem says that if A1 to AN are independent pi systems, then the sigma field generated by those A1 to AN are independent. So that's the pi independent system. The proof is a little bit analytical, and I'm not gonna present it here, but we're gonna use that in some of the corollaries. So one of them is very important, is that if x1 xn to x1 to xn, if the CDF of the joint probability is equal to the product of each CDF, and then x1 to xn are independent. The reason is we're going to use the independent pi system. The reason is that the collection of AI, where xi is less than or equal to some value r, for all r in the real line r, this is uncountable. Then this collection of sets, if A and B belongs to this AI, then A intercept B also belongs to AI, because xi less than or equal to x and xi less than or equal to y, the intersection will be xi will be less than the minimum of x and y. So that will also be belong to AI. So this AI is a pi system, and the sigma field generated by the pi system is the sigma field generated by the random variable xi, and by the theorem above, by the independent pi system, we have the x1 to xn independent. So the next one is if we have a series of sigma fields, Fij, I row and j column, Fi's, if they are independent, and let Gi be the sigma field generated by or the row sigma fields, so Fij for all j, then the G1 to Gn are independent. So this is also because of the so the proof. Let's look at the proofs here. So if we define AI to be the collection of or form of intersection of Aij for all j, where Aij belongs to Fij, then AI is a pi system that contains the omega and contains all the sets or in one of the Fij's. Um, so so AI so the independent pi system implies the sigma field of AI are independent. And then the another corollary is that if xij are independent and fi is a measurable function, then fi of each fi of x1 to x1 mi, those fi's are independent. That's also by which can be easily seen by looking at the sigma fields. If we define Fij to be the sigma field of generated by Xij, and Gi be the sigma field generated by each row Fij, then because Fi of those random variables are measurable under Gi, then the result will follow from the previous corollary from here, and that will prove that those Fi are independent. Now we finally come to our Kolmogorov 0,1 law, which says that if x1, x2, and so on are independent, and A is a tail event, then the probability of A is either 0 or 1. So to prove that, the idea to prove that is to prove that A is independent of itself. By doing so, then we can see that probability of A intersect of A is equal to probability A power 2, and hence for this to be to satisfy, then there has to be either 0 or 1. So that proves that PA is either 0 or 1. So now we need to prove that A is independent of itself. But to prove that, let's first look at the sigma fields. If we separate the random variables by any k, then sigma field generated by x1 to xk and the sigma field generated afterwards are independent, which are coming from the corollaries we see from the corollaries and the independent pi system theorem. So these two sigma fields are independent, and also the tail sigma field is a subset of the sigma field of xk plus 1 and so on, and it's true for all k. Therefore, the tail sigma field T and sigma field of generated by x1 to xk are independent for all k. And then because tail T is independent of these for all k, then if we generate if we generate a sigma field from those sigma field x1 to xk, then this is so the collection of those is gonna contains this sigma field of x1, sigma field generated by x1 to x2 and so on, then this will be independent with the tail sigma of t. Therefore, so we have this one is independent of the tail sigma field, and since the tail sigma field is also included in this x1 sigma field generated by x1, x2, and so on, then if A belongs to the tail sigma field, A also belongs to this sigma field generated by x1, x2, and so on. So we have concluded that A is independent of itself, and that proves the Kolmogorov 0,1 law.